Okay, so this lesson is on two theorems, the squeeze theorem and the intermediate value theorem. Let's actually start with what the squeeze theorem is. So what I have here is I have three different functions, and I'm going to call my top function g of x. I'll call the function that's being squeezed in the middle f of x, and then I'll call my lower function g of x. So basically what's happening is, oh, sorry, h of x. This would be h of x. So within my three functions, my h of x function is less than or equal to my f of x function, right? So f of x is greater than or equal to h of x, and f of x is less than or equal to g of x. What happens is if we take the first function, so I'll take g of x, and I say the limit as x approaches a of g of x. If that is equal to, so as I approach this a value here on g of x, if it's equal to the limit as x approaches a on h of x, and that is equal to L, so the limit as x approaches a on g of x is equal to the limit as x approaches a on h of x, right? The limit is L. Then what we could say is, according to the squeeze theorem, the limit as x approaches a of f of x is also equal to L. So if the limit as x approaches a of g of x is equal to the limit as x approaches a of h of x, then according to the squeeze theorem, the limit as x approaches a of f of x, because it's being squeezed in between these two functions, it's going to have the exact same limit. Okay? So let's prove this, or let's use the squeeze theorem to show this. I have three different functions here. So f of x is less than this function here. So we'll call this function our upper function, and my upper function would be g of x. We don't have to do this every time, but I'm just going to say that that guy is g of x. So f of x is being squeezed between g of x, and this one would be h of x. And we don't know what this function is, but we're going to use the squeeze theorem to evaluate this, the function in between that's being squeezed by g of x and h of x. So the first thing we do is we're going to apply the limit to every single expression. So I want the limit as x approaches 0 of f of x. So I'm going to apply that same limit to each expression in the inequality. So I'm going to say the limit as x approaches 0 of 8 minus x cubed is less than or equal to, this is the limit that I'm trying to evaluate, the limit as x approaches 0 of f of x, and that is less than or equal to, I'm going to apply the limit to every expression in the inequality, the limit as x approaches 0 of 8 plus x cubed. Once I apply the limit to each expression in the inequality, I'm going to evaluate the limit. I'm going to use direct substitution to figure out, well, what would the limit be of this function as x approaches 0? So using direct substitution, I would have 8 minus 0 cubed is less than or equal to the limit as x approaches 0 of f of x is less than or equal to, use direct substitution to evaluate this limit, and I get 8 plus 0 cubed. Okay, my lower limit, or sorry, my lower function, the bottom function, is approaching 8 on the y-axis. That's going to be less than the limit as x approaches 0 of the function being squeezed, and that is less than 8. What is the only number that I could put into this middle that would satisfy this inequality? So for example, I can't put the number 7 here. 7 is less than 8, but 8 is not less than 7. Do you know what the only number I could put in here is? 8. If this limit is 8 and this limit is 8, then even though I don't know what this function is, it's being squeezed by these two, so the limit of this guy would also have to be 8. So how we would write this, though, according to the squeeze theorem, is we'd say the following. We'd say since, now this function here I called h of x, so I'd say since the limit as x approaches 0 of h of x is equal to, it was equal to this limit as well. So the limit as x approaches 0 of g of x, that was equal to 8, right? So this limit and this limit equaled 8. Then according to the squeeze theorem, I could say then what I know is the limit as x approaches 0 of f of x is also equal to 8. This is what I was trying to solve. I wasn't given the function. I have no idea what it looks like, but I know that the limit's going to be 8. Okay, so let's do this guy. First step is to apply the limit to every expression in the inequality. So the limit as x approaches 2 of 5x plus 2 is less than or equal to the limit as x approaches 2 of my middle expression is less than or equal to the limit as x approaches 2 of x squared plus 8. So apply the limit to every expression in the inequality, and then you're going to evaluate each limit at that a value, which is 2. So 5 times 2 plus 2 is less than or equal to the limit as x approaches 2 of f of x is less than or equal to 2 squared plus 8. 4 plus 8, 12. So according to the squeeze theorem, Sarah, what would the limit as x approaches 2 of f of x be? It'd be 12. Yeah. So what I'll do is I'm going to call the upper function h of x, and I'll call this guy g of x. It really doesn't matter. I just can't call it I have to choose different functions other than f of x. So my justification would be since the limit as x approached 2 of my first function, which would be my lowest function, is equal to the limit as x approaches 2 of g of x, and that limit, both of them had a limit of 12, and according to the squeeze theorem, we would say the limit as x approaches 2 of f of x is going to be 12. Okay, let's look at what will happen with trig. So the limit as x approaches 0 of x times sine of x, and it says use the squeeze theorem to determine. So let's just draw to remind ourselves what the graph of y is equal to sine of x looks like. So the graph of y is equal to sine of x, remember it's goes through the origin. This would be one period. What's important though for when we do trig is we have a max of 1 and a min of -1. So I'm always going to set up my trig functions to be the same. Okay. So what happens is even though it says x sine of x, you're just going to take what the trig function is, and we're going to say that we know that this graph of sine of x, do you agree it is always between 1 and -1? Unless I change the amplitude of the graph, like the a value in front of sine of x, my sine of x graph is always between 1 and -1. Well, I need to get this function to not just be sine of x, I need it to have an x in front of it. So what I'm going to do is I'm going to create a bracket here, and I'm going to multiply every expression in the inequality by x, because what I'm really trying to determine is I want this to be x sine of x. So when I multiply an x in here, I'm going to get negative x is less than or equal to x sine of x is less than or equal to x. So I took this x, I'm going to multiply it inside. Then what we do is we're going to take the limit of each expression within our inequality. So I'm looking for the limit as x approaches 0. So I'm going to say, okay, the limit, so for this expression here, take the limit as x approaches 0 of negative x is less than or equal to the limit as x approaches 0 of x sine of x. And that is less than or equal to the limit as x approaches 0 of x. So now what I've created is I've created what they originally were looking for. The limit as x approaches 0 of x sine of x right here. Okay, we're going to evaluate each limit. So put in a 0 here. Negative 0 is the same thing as 0, is less than or equal to the limit as x approaches 0 of x sine of x, less than or equal to, input is 0 by substitution, and we get 0. So based on the squeeze theorem, we could say Akil, the limit as x approaches 0 of x sine of x, what is it equal to? It's equal to 0. Okay, let's do the same thing for, let's actually skip this one, and let's do number 5 next. It's a trig function, and it's sine. So what we do when we have trig functions is I know that the sine of n, a sine graph, we always say is between 1 and negative 1. Then I say, what am I going to multiply this expression by? Because what I want to get is I want to get 1 over n squared times sine of n. I already have the sine of n here, but what I want now in front of it is I want a 1 over n squared. So in order to get that there, I'm going to create a bracket, and I'm going to multiply the entire inequality by 1 over n squared. So when you multiply 1 over n squared and you distribute it in, I'm going to have negative 1 over n squared is less than or equal to the, it's less than or equal to 1 over n squared sine of n. And that is less than or equal to 1 over n squared. So I'm just going to look at this is what I'm trying to evaluate using the squeeze theorem, and does it match up here? It matches. So now take the limit of each expression within your inequality. So we got to take the limit of each. So the limit, and this time we're approaching infinity. So the limit as n approaches infinity of negative 1 over n squared is less than or equal to the limit as n approaches infinity of 1 over n squared sine of n is less than or equal to the limit as n approaches infinity of 1 over n squared. Okay, from the unit we just did, limits, let's evaluate this right-hand limit. 1 over super big number, what will this limit approach? Or, sorry, what will this limit? It'd be 0. Or you could say the degree of the top is equal to, is less than the degree of the bottom, right? This is going to approach a horizontal asymptote, y is equal to 0. Or you could have evaluated this by dividing each term by n squared, right, from limits to infinity, and we would get 0 here. And then same over here. Negative 1 divided by infinity is 0. Okay, so I could say, according to the squeeze theorem, the limit as n approaches infinity of 1 over n squared times sine of n it is equal to 0. All of these limits for these trig ones actually equal 0, but you just have to be able to show the proof working through it. Okay, let's do the cos one. It's going to be the exact same as sine. It's no more difficult. Let's just quickly write the graph of y is equal to what the cos of x is. Now, the graph of y is equal to cos of x, we know that it starts at its peak. But what we really need is what the amplitude of this graph is. And the amplitude is between 1 and -1. Now, some students would say, well, what about like the function that we're given is 1 over x? The amplitude of this graph is, there's an invisible 1 in front of it. So this, even though this is going to affect the inside this function is going to affect the period. So what's going to happen is it's still going to go from 1 to -1, and it will just maybe oscillate, like it'll be much more compressed when we have this inside the functions affecting the period. It doesn't matter. You take this, the amplitude is still 1. So what I'll say is I'll say cos of 1 over x, it's going to be just like sine. It's between 1 and -1. And then you say, I need to match it up to have this function here. So I'm going to multiply everything by x cubed to get -x cubed less than or equal to x cubed cos of 1 over x less than or equal to x cubed. Take the limit of each expression within the inequality. This one, x is approaching 0. Do your direct substitution. Maya, what would the limit of that function be approaching? 0. Okay. So that's a squeeze theorem. And so I gave 4 practice problems in your AP workbook for the squeeze theorem. Let's do the intermediate value theorem. Next. Okay, so the intermediate value theorem is, we're going to shorthand it just by writing the IVT. And the intermediate value theorem is going to be applied for continuous functions. So most of the functions that we're going to be seeing today is going to be polynomial functions. Now, I'm going to draw a polynomial function here. I don't want you to draw it. I'll show you what I want you to draw from it. But let's say like this would be an example of a polynomial function. This is a continuous function. All polynomial functions are continuous functions. So what's going to happen is we're going to look at a piece of this function. So when I say we're going to draw something, I'm going to look at maybe that piece of the function there. So what I want you to draw is I want you to draw a piece of a polynomial function, and let's sort of have it look like this. Just imagine that this is a piece of a polynomial function. Polynomials are continuous though, okay? So the first x value, this point here on my function, I'm going to call this a. And if that's a, this y value would be f of a. It's going to continue my function to this point here. So I'll call this point b, which means that the corresponding y value would be f of b. Okay, So the first thing is we've got these three conditions that need to be met for the intermediate value theorem. The first condition is the function is continuous on an interval. Now, the interval for this would be from A to B. So it would be the closed interval A to B. Closed intervals, you guys, means we have squared brackets, means that A is included in the interval to B. Okay? Then the second part of the intermediate value theorem, it's basically saying that one y value is bigger than the other. So in this case, f of b, do you guys agree it would be f of b is less than f of a for this one? So f of b is less than f of a, or we could have the opposite, and f of a could be greater than f of b. Is all this is saying is within our function, one y value is bigger than the other. So that's what we're going to see. What we're going to do is we're going to introduce a random point, f of c. Okay? And f of c always has to be between f of a and f of b. So f of c has to be somewhere between. So I'll put f of c between. If it's between, do you agree? Okay, so it says, according to the intermediate value theorem, there's going to be a value of c. This is going to be my value of c, such that f of c is equal to some number. So like f of c would be, this would be c right here. And do you agree that c will be between a and b? That's what we're going to be proving with this intermediate value theorem. This number is going to change for every question. So it changes for every question. And it's going to be what we're trying to determine. And what happens is if f of c is between these two y values here, what that means is this c value is less than b, but it's greater than a. It's going to be in between, somewhere between a and b. Okay, so let's look at this first example. It says use the intermediate value theorem to show that there is a root or a zero. So remember, a root or a zero is an x-intercept of this given equation within this interval here. Okay, so the first thing is as follows. We can only use the intermediate value theorem on continuous functions. This is a polynomial. Is this continuous? Yes. So what we state for these questions is we're just going to state that f of x is a polynomial. Therefore, f of x is continuous. It says all polynomials are continuous on, this is the interval that we're looking at, my polynomial from 3 to 5. This is like my a value, and this is my b value. So when we're going to look at this graph from x is equal to 3 to x is equal to 5, that little piece of the graph. Okay? What we need is we need to find next what is f of 3 and what is f of 5. So we need to find, this would be like f of a and f of b. We need to calculate what f of 3 is and what f of 5 is. So f of 3 would be 3 squared minus 3 minus 12. F of 3 is 9 minus 3, 6 minus 12, negative 6. Are we good with that? Okay. F of 5 would be 5 squared minus 5 minus 12. F of 5 is going to be 25 minus 5 is 20. 20 minus 12 is 8. Okay, so let's visualize this on a graph. So f of 3, 1, 2, 3, 4, 5. Okay, so f of 3. Don't worry about like -6. Let's just put that down here. So there's f of 3 is -6, and then f of 5 is 8. That would be up here. What this question is asking is, according to the intermediate value theorem, or use the intermediate value theorem to show that there is an x-intercept within this interval here. So you guys, first of all, if we're going from -6 to 8, we always look at the y values, like when we don't sketch them. So we're going from -6 to 8. When I connect these 2 points, am I going to have an intercept, a 0? Yes, this is going to be a polynomial function, right? So these 2 points are going to be connected, and I am going to have a 0. What we're going to show is there a 0 between 3 and 5? So is our 0 going to be between 3 and 5? So first we have to say that the function's continuous. Then we have to show what our f of a and our f of b is. And now what they want us to show is f of c is equal to, they want it to be a 0, because that's what they're asking for. So we're going to show that f of c is equal to 0. So what we do is you're going to set your function equal to, because they want to prove that there's a 0 there, set equal to 0. So set your function x squared minus x minus 12 is equal to 0. Let's factor this function, and we are going to get x minus 4, and we're going to get x plus 3 is equal to 0. This polynomial function has 2 zeros. It has a 0 at 4 and a 0 at -3. Only one of these zeros, though, is within the interval. So one of them I'm going to not even talk about. It's going to get rejected. So which one would I reject? The -3. What we just calculated is actually our c value. So we just calculated our c value is 4. Is 4 within this interval? Yes. So we always put our c value in the middle, and I say, okay, that guy was less than 5, but it is greater than 3, so it's within this interval. And I could also say that f of 4, because I just calculated that this guy is 4, f of 4 is equal to 0. So this here will be 4. It takes a couple of these before you'll be like, okay, I actually see what we're doing here with this theorem. Let's do another one. Use the intermediate value theorem to find the value of c within this given interval. So first of all, is this function continuous? Yes, it's a polynomial. So we're going to state that f of x is a polynomial. We'll only be doing these for polynomials. Later on, I'll show you what we would do if they're not. But f of x is a polynomial. Therefore, f of x is continuous on that closed interval 1 to 4. So a is 1, b is 4. Okay, the second step is we always want to calculate what those 2 points are. So we want to calculate what f of 1 is and what f of 4 is. So f of 1 will be just 2 plus 3 plus 5. So what would f of 1 be? 10, yeah. So 2 plus 3 plus 5 is 10. F of 4 we'll actually have to calculate. So I've got 16 times 2, so I've got 32 and 12 and 5. So what are you guys getting? What is it? 49. F of 4 is equal to 49. Okay, so let's think about what this is asking first of all. My graph is going to go from a y value of 10 to a y value of 49, will that graph cut through a y value of 19 somewhere? Yes. Okay, so that's what we're going to show. So let's just do a little tiny sketch to sort of visualize this. And when you understand this, you won't even need to do the sketch, but f of 1 is 10. So 1, 2, 3, 4. I'm just going to put 10 here. This polynomial is going from 1 comma 10 to 4 comma 49. So I'll just have 49 way up there. So I'll go from here to here. What this f of c is 19 is asking is there going to be a c value? Like somewhere on here, when we go from 10 to 49, we are going to have a y value of 19. What was that x value that gives us this y value of 19, right? Because clearly, like 19, you guys, will be, let's say that this is 19. They want to know, well, what was that c value? Okay, so how we're going to now write this is I'm going to write f of c is equal to 19. And 19, we're looking at the y values. 19, it is a number less than, it's less than 49, greater than this y value of 10. So what that means is we can apply the intermediate value theorem, and we could state that c is going to be less than, do you know what I would put over here? So c would be, yeah, c would be less than 4, and it would be greater than, Sarah, what number? So c, we're going to find this value c that has a y value of 19. It's going to be less than 4 and greater than 1. Yes. According to the intermediate value theorem, c will be less than 4, greater than 1. How do we find what c is? We take our function and we set it equal to what number? Not 0, because that would be finding zeros. We set it equal to 19. So we take our function, 2x squared plus 3x plus 5, and you set that equal to 19, because I want to figure out what is the x value when c is 19. Or sorry, what is my x value when what is my x coordinate when y is 19? Okay, let's bring 19 over to the left. So let's subtract 19, and we're going to get negative 14 is equal to 0. Normally, we would do factoring by decomp. Are you okay if I just give you what the two factors are? Okay, so if you saw this on an exam, you'd be doing decomp, but we'd have 2x plus 7 and x minus 2 is equal to 0. On this parabola, there's two x coordinates where y will be 19, right? My y value is 19. The x coordinates are negative 7 over 2 and 2. What that means is I was looking for which value of f of c would be 19. Which answer would it be? It's got to be within the given interval of 1 to 4, so it's not going to be this one. That's going to be my c value. C is going to be equal to 2, and what I could say is f of 2 is equal to 19. So what that means is this graph is slightly off. This is my c value. 19 would be right there. Okay. Let's do one more like this, and then let's look at table of values. If f of x is equal to the following function on that interval, verify that the intermediate value theorem applies to the indicated interval and find the value of c guaranteed by this intermediate value theorem. Okay, so state that it's continuous because it's a polynomial. So f of x is a polynomial. Therefore, we can only use the intermediate value theorem on continuous functions within that interval. So therefore, f of x is continuous on the closed interval. We're only looking at the graph from 0 to 5. You need to find what f of 0 is, and you need to find what f of 5 is. So take a minute, find f of 0 and f of 5. F of 0 will be the easy one to find. F of 5. So f of 0 is -1, and f of 5, oh, and do you have f of 5? 29. Okay, so picture the y values of this graph. We're going from -1 to 29. Will that piece of that graph have, is there going to be a place on my graph where we're going to go through 11? Yes, right? When we go from -1 up to 29, we will have cutting through -11. So again, if you need to see that sketch, what the sketch would be, f of 0 is -1, would be right down here. F of 5, they're saying it's 29, so that would be up here. When we go from -1 to 29, there is going to be, like this graph, somewhere on this graph, we're going to have a y value at 11, and we want to calculate what is that corresponding c value, which is the x value, is what we're calculating. Okay, so then we could say we want to talk about this value here. 11 is less than 29, and it is greater than -1, which means that the c value, so wherever 11 is, the c value is going to be less than, Carly, what number? And greater than 0. Okay. So now we could apply the intermediate value theorem to the function. So we take our function and we set it equal to, Emily, what would I set this one equal to? I'm trying to find when on my function it's going to go through. Yes, you set it equal to this. If it was asking like when is it going to have an x-intercept, you set it equal to 0, but we're setting it equal to 11. So subtract 11 from both sides, and we're going to get -12. We're going to be able to factor this, and our two factors will be x plus 4 and x minus 3. X is equal to -4, x is equal to 3. Within the closed interval given, I'm not even looking at this -4 because that's not within 0 to 5. That would be my c value. So at 3, I guess it would be down here, that y value would be 11. So at 3, the y value is 11. So we would say c is equal to 3 and f of 3 is equal to 11. On AP exams, they will often give tables that look like this, and you're going to be answering questions on the table. Okay, so this is where you need to be sort of good at visualizing things. So it says on the interval 0 to 9. So 0 to 9. What is the minimum number of zeros? So first of all, it tells me that my function is continuous, so we could use this intermediate value theorem. So as we go from 0 to 9, what is the minimum number of zeros that this graph could have? So what we look at is we look at the y values. So let's look at the y value. We're going from 1 to -5. So picture a y value of 1 and then a y value of -5. Will we have a 0 at least in between 1 and -5? Yes. right? If you had a y value of 1 and you got to go down to a y value of -5, you're cutting the x-intercept, the x-axis, which is going to be a 0. So we're going to have a 0 here. Then you're at -5 on a y value, and you're going to go up to a y value of 3. Would our graph go through another 0? Yes, we would have a 0 here. From 3, we're then going to go up to 7. What would you guys say? No. Now, I'll show you later on that maybe from 3, like, there's no guaranteed 0 here, because I'll show you how maybe there could be, but it wants the word minimum. Okay, so I'm going to say no there. As we go from 7 to -1, so y value of 7 down to y value of -1, are we guaranteed to cut the x-axis? Yes. So we're going to have a 0 here. So the minimum number of zeros on the closed interval 0 to 9, 3 zeros. Okay, on the interval 4 to 9, so this interval would be 4 to 9. What is the fewest possible times that we would have a y value of 1? So let's look at 4 to 9. So I'm going to erase this. Okay, so you guys, if we're going from y values of 3 to 7, are we going to have a y value of 1? No. As we go from a y value of 7 to a y value of -9, or sorry, -1, are we going to have at least a y value of 1? Yes. So the answer for this one is once, one time. Fewest possible, one time. Okay, on the interval 0 to 4, must there be a value for x for which f of x is equal to 2? Okay, so let's think about this. On the interval 0 to 4, so on the interval 0 to 4, our y values are going from 1 to -5. That is not, we're not going to be cutting, when we're going from 1 to -5, we're not going to be cutting 2. But as we go from -5 to 3, are we guaranteed to have a y value of 2? Yes. Now, how would we write this if this was like a free response question on your AP exam? So because it says the word explain, this is what we're going to write. We always start with f of x is continuous, right? So f of x is continuous on the interval 0 to 4. We were told that in the initial question. Then we have to talk about, remember, we always talk about points. So we always talk about f of a and f of b. So f of 0, what's f of 0 according to my graph? Or f of 0 is 1. And f of 4, Shewa, is what? Is 3. As we go from 1 to 3, we are going to be cutting through 2, right? So how I would say that is I would say they're asking for 2. So remember that 2 is less than this y value, but it's greater than this y value. Oops, that would be a 1 or 0, a 1. So what that means is we could say we know that there's a c value less than 4, greater than 0. And how we'd write this as a sentence is according to the intermediate value theorem, so according to the IVT, there is a value c such that f of c is equal to 2, because we know if we're going from 1 to 3, we're going to be cutting a y value of 2. and then we say that this inequality again, c is less than 4 and greater than 0. Okay, this guy on the interval 4 to 8. Could there be a value for which f of x is negative 2? So let's write that sentence. F of x is continuous on the interval 4 to 8. Then I need to find what f of 4 is, and I need to find what f of 8 is. So Abby, what's f of 4? Yes, f of 4 is 3. And Shaywa, what's f of 8? 7. Okay, so some students would say when you go from 3 to 7, we're not going to be going through negative 2, right? But it says the word could. So here's what I want you to draw. I want you to draw those 2 points. When x is 4, y is 3. So let's just draw x is 4, y is 3. So just draw that point. And x is 8, y is 7. So draw that point. We don't know what the function looks like, right? If it was a polynomial, these would be connected in a nice smooth curve. But could I connect these 2 dots and somehow my function dips below and is going to cut through negative 2? Yeah. So like I could draw this, right? And even though negative 2 is not between 3 and 7, I wasn't given what the function looks like. There is a possibility that my function could have a y value of negative 2. So what we would say for this one is there is no guarantee. Okay, so we'd say there is no guarantee that f of x is equal to negative 2. Right? There's no guarantee, because if it's a polynomial function, it's not going to go through negative 2 between that interval. There's no guarantee that f of x is equal to negative 2, but f of x could be negative 2. Right? So because I don't know what the function looks like, this is an example where it could be. So this was like, could it be? Okay, let's do this last one. Will this function ever equal 8 on this interval? State what first, Julie? Yep. Why is it continuous? Yes. F of x is a polynomial. Therefore, f of x is continuous on that closed interval, negative 1 to 5. Next, we're going to figure out what f of negative 1 is and what f of 5 is. And to speed it up, I'll just give you those numbers. F of negative 1 is equal to 3, and f of 5 is 21. So this polynomial graph, the y values are going from 3 to 21. Will that graph ever equal 8, the y value of 8? Yes. Okay. So I know that 8 is less than 21, greater than 3. So there's going to be a c value less than 5, greater than negative 1. How you figure out what that c value is you set your polynomial. I want to know, when is this graph equal to 8? Because basically what I'm trying to find, this equal to 8 is f of c is equal to 8. I want to find when is my graph cutting, has a y value of 8. So bring your 8 to the left-hand side, and we're going to get, oh, I guess we don't even have to, they weren't actually asking for that because we won't be able to factor. We won't be able to factor this. Minus 7 is equal to 0. The question is, will the function ever equal 8 on this interval explain? Okay, so our sentence where we're going to end this is according to the intermediate value theorem. Do we agree there's going to be a value of c? Yes, there is a value of c. There is a value of c, right? If we can't factor this, they're not going to ask on a test what it is. They'll just, you need to explain, such that f of c is equal to, what would f of c be equal to? 8. And c is between which two numbers, Akil? Yes. The intermediate value theorem will guarantee that. Okay? There would be 4 of these little questions to do in your AP workbook.